All right, so circuit breakers and fuses. All right, now let's go ahead and start this presentation. So, circuit breakers. All right, I hope that you guys know what they are. All right, you see probably this type in your house, something that looks somewhat like that in your house if you go to your main breaker panel. All right. And depending on your household and all those other wonderful things, there may be a few of them, there may be a lot of them. All right. Or if your household is really old, you're going to see a fuse in there. All right. It's going to be just basically a little circle. And if you take it off, and we'll see a picture of this later, but it will look something like this with some threads on there. All right, and that'll be a fuse if you look at it from the side view. But anyway, um, we all have circuit breakers in your house. Probably many of you have tripped your circuit breakers. All right, um, in the wonderful world of tripping. Now, the real question here always comes down to why do we have circuit breakers? All right, that is the biggest question that you probably are asking yourself. All right, does anybody know the answer? That Ethan?
I think it's so you don't put too much strain on the current you're using.
Yeah.
So
Okay.
nothing basically like catches on fire.
Excellent. All right. So fire prevention. Now it's not direct fire prevention, right? It's not like it's going to put out a candle if you name it. But you did mention current, which is great. All right. So circuit breakers are rated in the amount of current they can carry. All right. And on this one, it's right here on the little flipper knob. All right. So this one would be capable of carrying 20 amps of power. All right. So that would be our little switch to turn it on and off. And you can see that we do have a on section at the top here, and we have an off section at the bottom. All right. So on and off. There's actually a third position in the middle, but we'll come back to that one in a minute. So the current rating, that's going to be probably the most important aspect of these. All right. Um, and as Ethan did mention, it's help preventing fire. All right. Now, when we say how circuit breakers are preventing fire, all right, it's meant that they're there to protect, help you prevent electrical fire, to be more exact. All right, um, so that is the whole point of them. Um, and I actually have witnessed this very recently. It was in December. See if I can find those pictures. But anyway, this wasn't a direct fire incident, but it was definitely one of those like, oh, I don't know what's going on here, and I don't know if I really want to be modifying this or playing with this, those types of things. Um, but there's some craziness that can go on. All right, so let me go ahead and there we go. You guys can see that already. Good. All right, so here you can actually see this is a breaker panel box. Not a breaker panel box. Sorry, this is a thermostat for an HVAC system. Um, and man, the wires in there are all toasty, and the back is melted. And I mean, here, right there, you can actually see a broken wire. This was not a wire that I took a wire nut off of. This was a wire that actually melted its way through. You can see all the like a smoke and fire kind of damage. It looks like that's going on in there. There you can see kind of far out view of it. I think if I remember correctly, this wire, yep, that wire right there was exposed copper. All right, there was no more sheathing on it. So the whole point of the circuit breakers is to help protect against those types of things. All right. Um, is it an end-all solution? No, you still do need to be careful with your system and make sure that there's no major damage or anything like that that is going to go on. So a little bit of a give and take going on there. But just something that you do want to be aware of right there. Now, um, so circuit breakers, they're there to help prevent fire. Now, some people do get this a little bit mistaken. So the whole point of a circuit breaker is to keep the wiring in your house from catching on fire. All right. Um, for those who do not know, in your house, your main electrical wire. I guess I should do this with the right colors because well we can. Let me select the colors here. All right. So now it's gonna be kind of hard. All right. Well, we have three wires in your house. One, two, three. That basically run to everything. I can't do this because of white. But anyway, we have not a red wire, Greg. Come on. What? Let me do this button. There we go. Now I can do this. Nope, it won't let me draw on that. That's annoying. All right. Anyway, um, we don't have a red wire. We have three wires. We have black. Let's just change colors. We have a black wire. You have a white wire, and you have a green or a copper wire. So either it's green, it has a green coating, or there's no coating at all, and it's just bare copper. All right, so it's green or copper. All right, the white wire is what's called our neutral. We'll come back to this probably next class. Our black wire is what we like to call the hot wire, and then our green, this is our ground. All right, and normally those three wires are all individual sheaths, so they've all got their own protective wire coating on them. They're all insulated, and then those normally all are then in another white wire, white coating. All right, so there's actually three different coatings going on. Not of which that you can see here. I don't see that in there, but you can see the black wire. You can see a white wire. So you can actually see this. This one does have a red wire. This is a little bit of an abnormal install because this is meant for a heater instead of a 120 circuit. But anyway, so we do have three different color wires and those types of things going on. So circuit breakers are meant to protect that type of wire. All right, the type of wire that is physically built into your house. All right, the stuff in the walls. It does not truly protect from your wonderful little outlets, right, to whatever lamp or whatever thing that you have plugged in. All right, it does not actually protect from that outlet to the lamp. All it does is protect from the outlet to back to the circuit breaker. Now, when I say protect, all right, it will still trip if this is over the magical, in this case, 20 amp rating that is over here. All right, it will still happily trip in that instance. All right, but that's not what I mean by protect. All right, this breaker you will have to rate for whatever size wires you have run inside your house. All right, so the wires that are in your wall, and the most in household, the most common are either 14 gauge or 12 gauge. All right, those are our two most common wire sizes. 14 gauge is rated for 15 amps. Anyone know what 12 gauge is rated for? All right, it is rated for 20 amps. All right, so those are the most two wires, or most often used wires that you're gonna see. So that is something that you do kind of just want to be aware of. Um, so whenever you're doing modifications to electrical or things like that, you do need to take those considerations into effect. All right, you need to think, okay, it's a 14 amp circuit, it's going to have 15 amps, or 14 gauge, or is this a 12 gauge? Basically all your outlets should be 20 amp, and your lights should be 15 amps or thereabouts. All right. And again, this is not a perfect system. This is especially not perfect in households where people do their own electrical wiring and they don't really realize this. And they're like, oh, there's a light right there. I can pull it. I can go to an outlet. It'll be fine. Yeah, it'll be fine as long as you haven't gone down a wire size, and as long as you don't plan on putting a large load on that, everything will be just dandy. All right. What caused the issue in these pictures that I was just showing you guys, all right, was that there was two big issues. The first issue was not the way I wanted to go. Let's go back this way. First issue was that the wires and the circuit breaker in the cabinet were 20 amps. So in the breaker panel, it was a 20 amp circuit. All right. But the real issue was that the thermostat down here was only rated for 15 amps. All right. Now, why this worked for years and years and years and then all of a sudden had problems? I have no stinking clue. All right. I don't know when this thermostat was installed, but it was installed a long time ago, as you can probably tell somewhat by the discolored paint, things like this down there. But it was installed ages ago, and it worked fine for many, many, many years. And then one year, the heater stopped working in the living room. All right. So that's one of those things that you do need to kind of keep in the back of your mind. But probably what happened over time was we just kept pulling more and more and more power from the thermostat, and that was causing issues. And while the wires going from here, that wire nut, back to the circuit breaker were of that 12 gauge variety, which are meant to carry that 20 amps, the wires that connect from the wire nut to the thermostat itself, these red wires and black wires you see right here, those were probably only 14 gauge. All right, because this thermostat was only rated for 15 amps, so it didn't need to have those larger wires. So um, that caused some slight problems of those wires meltings, and that caused some problems. Luckily, the house didn't burn down. Um, Probably there was something funky going on there for a while, but everything overall was actually fine. So that was a good thing. So circuit breakers are meant to protect um, your house overall from burning to the ground, from the electrical wires in your house short circuiting and causing an electrical fire. That is their main purpose. All right. Now, there are two different types of tricking mechanisms that should be built into your circuit breakers. All right. And those two would be a thermal trip and a magnetic trip. All right. Now, let's just go to the next slide and we will continue talking about those trips because you can then see a picture. All right. So here we have a bunch of different parts of a circuit breaker. Now, this is not a US circuit breaker. This is probably more of a UK, maybe Europe style. It's meant to be mounted to a DIN rail, and what that means is a DIN rail is basically this little like C shape that would go in here. All right. So that way the circuit breaker would hook on the top and then it latches on the bottom normally with something like that. That holds it in, and if you ever need to replace it, you can pull the little latch away this direction, and then you can pull the circuit breaker off, slap a new one in, connect your wires up, and you're good to go. So not a US style here. I like this style. You might see it in industry on some DIN rails. That's where a lot of DIN rails are, but not a standard US style. But anyway, let's go through these parts real quick. So we have up here at the top, we have our actuator level. All right, nothing too fancy about that. Basically the same thing that we have on the US ones. All right. Right below that, we have our mechanism. So this is what actually allows this, when this is flipped this way, to latch and then to also be tripped in case of it being needing to be tripped. All right. We've got some contacts here. All right. So when you flip this lever in that direction, this mechanism right here moves that way until basically those threes are touching. And that is actually what's creating the circuit. That is the actual switch part. All right. That is what allows this whole thing to work. All right. If you look very closely, we'll come back to that. So we have our contacts. Up at the top, we have a terminal. All right. So this would be, say, going out to your lights. Hold this still. And this would be going back to your main breaker or things like that. And again, US style like this, we don't actually have the second terminal here. All right, this actually lives down here, and it sticks out the bottom. So when we stick it into our breaker panel, it actually automatically connects the one side. So we only have one screw terminal. We have our bimetallic strip. All right, and that is going to be one of our trip mechanisms. So right here. All right. And basically what a bimetallic strip is we have bi means two, all right? So we have two different types of metal, all right, that they have welded together at the top. All right? And hopefully you all know this, but if you don't, when metal gets hot, it heats up, it actually stretches. All right? And because these two metals are dissimilar, they stretch at different rates. All right. So this one might stretch, 1 centimeter per 1,000 degrees or whatever, and this one might only stretch, a quarter of a centimeter per 1,000 degrees. And because of that, as this stretches and that one, or as the red one stretches and the blue one doesn't stretch as much, this thing will start to arc. I just realized I did that with the wrong color. So let's go ahead and erase all the ink. So that bimetallic strip is going to want to arc. All right, so that red one's going to get longer. So instead of it being all the way out here, it's now stretched and stretched and stretched. All right, or flexed per se. All right, and that actually trips the actuator mechanism up here. All right, I have some videos for you guys to watch after class, so that way you can kind of see how the whole tripping process and things like that work. It's actually, these things are really neat in my opinion. I've got some fun videos. But anyway, so there's a little bimetallic strip there that will flex, and it's not going to flex that much. I've got this drone a little bit too crazy, but it flexes just enough to push a little lever, which causes this mechanism to release and fall and do whatever it needs to do. All right, so that's what our bimetallic strip is. There is also a calibration screw, which you can see here. All right, this is not normally accessible by us PC, little minions, little humans that live in the households. This is more for the factory and things like that, and that allows them to tweak this bimetallic strip so it actually trips at the right point. All right, so that's what that calibration screw is for. So the bimetallic strip, this is what I'd qualify as the slow blow of the fuse world. All right, let's say this breaker is rated for 20 amps. All right, if you would pull 21 amps through it, it's going to trip, but it might trip after a minute or 5 minutes or whatever the magical number is. All right, so it's not going to trip instantly at 21. It's not going to trip instantly at 22. But as we keep increasing these numbers, our time decreases. Our trip time. All right. So as our amperage increases, that means we're putting more and more and more and more and more heat into this bimetallic strip because it's a resistive element. So there's current flowing through, which is causing a voltage drop, which is causing heat to build up. As we do that more and more and more, that strip is going to flex quicker, quicker, quicker. All right. And by it flexing quicker, it's going to trip quicker. So that is one of those reasons why if you're ever using like a circular saw or a chop saw or something, like a very high power device, and man, we're talking very, very high power here. All right. Just a fun little side note. If we have a 20 amp breaker and we are rocking 120 volts through it using Watt's law, that's 2,400 watts. All right. Now, if you're only using a 15 amp breaker, right, that's only going to be 3/4 of that. That's only going to be 1,800 watts. So if you put a 2,000 watt circular saw or whatever on this thing, over time, we're going to pull way too much power. Not way too much. We're going to pull a little bit too much power. But over time, that if we're doing a 15 amp breaker, that is, all of a sudden you're going to be using your saw, you're going to be cut, and then all of a sudden the breaker's going to trip. You're going to be halfway through your cut, and you're like, why did it trip now? Like, why didn't it trip when I first started cutting? Well, as you tried to cut faster or whatever with the circular saw, you put more load on it, which meant the wattage went up. And again, you're not like overloading the breaker super hard. You're just kind of doing a slow overload, which means that bimetallic strip had to heat up. That's also the reason why if you just go reset the breaker right away and then you try to cut right away again, it's actually going to trip quicker because normally that bimetallic strip hasn't cooled all the way down yet, so it hasn't completely reset. So you're starting from our already pre-warmed position. All right. So that is what the whole point of that bimetallic strip is. Now the other option that you have for tripping, all right, is the solenoid. All right, and that would be up here. All right, and for those who don't know what a solenoid is, it's basically an electromagnet. All right, so as current flows through this coil of wire, all right, it's becoming an electromagnet, and the more current you flow through that, the stronger it gets. And if we do a little cutaway here, just assume that we've cut this thing
We're
perfectly.
still looking at the calculator.
Thank you. Yeah, I even have that screen open in front of me, so I would like see that fact, but still miss it. But anyway, 7 is our. Well, there we go. 7 is our solenoid. All right. So we have a whole bunch of different coils. All right, and I'm going to draw this like we cut the thing in half. All right. So we have our coils. And in theory, in the background, those would all be connected together, right? So we can't see through this. But anyway, you got the idea. There is a slug of steel in here, and you can see there's a pin sticking out of that solenoid. So that would be that pin. And then there's going to be a spring here. All right. And as we put more and more power through that coil, this is moving that way. All right, so at 21 amps, it can't fight that spring very much. But as we get to like 40 amps or 50 amps or 100 amps, that spring is just worthless. All right, and it pushes this thing down, which extends that pin out, which again hits that actuation level or that actuator mechanism, number 2, and it causes it to trip. All right, So our solenoid is going to be what I'd call the fast blow or the instantaneous. All right, that is meant for when you take two wires and you just touch the hot wires together, you short through a complete and utter short circuit, or you pull way too much power off of the thing. It is just going to instantaneously pop, and the breaker's going to go, oh no, way too much power, and it's going to pop that. So your bimetallic strip hasn't even had time to heat up yet. All right, all it has had time to do is to just heat up just an itty bitty little bit. But in that case, normally you don't want to just wait for that thing to pop, but you want that damn thing to trip right away because that's a lot of current flowing. All right, so there is a lot going on here when it comes down to these solenoid or to these circuit breakers. The last item is an arc divider. All right, and as you can see, that's right here. Actually, before we get to the arc divider, let's go ahead and draw the path of electricity. So power flows in here. All right. We then flow down to our bimetallic strip. So we kind of actually flow this way. Then we flow back up to our contacts here. And then those contacts, if they were closed, would connect. And then we would flow through this solenoid, and then we'd flow out through that. So power is actually flowing both through the solenoid and through that, bimetallic strip. All right, so a little bit of a complex route to get through this whole thing. The other thing that I would like to point out is that right here, it's kind of hard to see it, but that is actually a braided copper wire. All right, so it's a very flexible wire, which is what allows us to have this contact right here moving. All right, without that braided copper wire, this would be too stiff and we wouldn't be able to move that contact open and closed. So, all right, but anyway, back to the arc divider. The whole point of an arc divider is electricity doesn't want to stop flowing. All right, and the higher the voltage, the more arc that you get. All right, so with 12 volts, if you ever like short circuit your 12-volt battery with a wire, you'll see some sparks. With 120 volts, you can actually start to get power to flow through the air between these contacts. So as those contacts are opening, there's going to be a spark, and you're actually going to see it. All right, it's kind of like a Jacob's ladder if you've ever seen one of those, where the power just kind of flows up and up the wire. And there's an animated. There. That's Jacob's ladder. That's what I want. Videos. All right. I just really want the quick video. Come on, let me pause this so I can get back. So there you can see.
This is a penguin.
I don't care about the penguin. But there you could see how the electric arc was willing to go up and up and up. And basically, as that arc started, as you notice, it didn't always go up to the same point. But as that arc started, all right, it was very small at the very bottom. And that arc was creating a lot of heat. It was ionizing that air, which then actually made it easier for the spark to jump through. And as it heated that air, it was then able to move up because it was easier for it to jump through and it wanted to move up. So it's constantly moving up, following that heat and ionizing air and everything else to the very top. So as we open that spark, all right, that spark wants to form, all right, and that's bad. All right, having an arc like that between your two contacts and things is not really good. And also remember, this contact here moves extremely fast. That thing is spring loaded. It's not like I'm just gonna half open this. No, normally it's a nice little clunk mechanism that like instantly latches that thing. But as you break that arc forms, and we don't want it to stay here. We want to dissipate that, and the easiest way to dissipate an arc is with more surface area, all right, and distance. So as you can see here, that arc then wants to move this way, all right, because that distance is smaller than this distance as it's opened. And then it actually arcs between this, and it constantly keeps moving, and it gets really big, and then we get all the way up to this point. And in an arc divider / extinguisher, there are a whole bunch of different copper plates that aren't actually connected to each other. But what that allows the arc to do is it actually takes that from one really large arc once it hits that, and it becomes very small little arcs. So instead of having this one arc that's say maybe an inch wide, it goes down to maybe a whole bunch that are 1/16 wide or something like that, with a lot of surface area on that copper, and that helps extinguish that arc. Right? So that arc is really important. You'll also notice that the back side of this is vented normally to atmosphere because of, again, all those gases and things like that. We don't want those getting built up in our circuit breaker, and if you get too much gases, that breaker is going to want to pop and expand and do funky things, so we don't want that to happen. So that would be the arc divider there in the back. So circuit breakers, you look at them, it's a little plastic box, you're like, wow, this thing is really complicated, and yeah, overall it actually is pretty complicated. Tab. All right, let's quick go back to this for a second. Here you can actually see a US style circuit breaker panel box. All right, so you would actually hook the circuit breaker in over here on the left hand side, and then you would push the back into one of these spikes. All right, and that is actually how we get power. So we'd have a screw terminal over here on the left, and then that actually latches into these metal bus bars on the back, which is actually, to me, an easier way to install them, having to wire the both a hot and a cold side to these things, which is kind of nice. Now, on this one, you will see that, notice that these spikes are every other breaker spot. So you could actually, in this breaker panel, we could have 1, 2, 3, 4, 5, 6, 7, 8 different breakers in this little breaker panel here. And that's 8 normal size breakers. And every other one connects the opposite side. So in the US, we actually have 220, 240, whatever you want to call it, because we have 120 from our neutral wire or ground to our phase 1, not phase 1, side 1, side 2. All right, we don't do phases in the US. We have single phase power at home. But we do have a split phase transformer. So you have 120 from the center tap to the left, 120 to the right, or 240 if you would put a multimeter between these two screw terminals. So when we're doing things that are much higher wattage, like baseboard heat, electric hot water heaters, and HVAC systems and things like that, we're running 240 volts to them, or 220 volt, which just allows us a little bit of buffer space. It keeps the wire size from having to be as big. Some countries, all they do is run 220, 240. They don't actually have that 120 at all. And I don't know if there's there's definitely a different safety issues there with the higher voltages. But in the long run, it's not really that hard to go, oh, do you want a high voltage or low voltage? It doesn't really matter. It's, what your equipment can run off is what it comes down to. In fact, a nice demo point of that, if you ever actually take a look at one of your cell phones, ever look at a cell phone charger, universal cell phone charger, and you look at the power rating on the back, it actually normally says it's good from like 90 volts to 250 volts or something like that. If I can find a good picture, and of course I cannot. All right, but anyway, most of them are universal. So even though they have the US plug on the back, it really doesn't matter what style or where you plug it in. You just get one of those really cheap converters that just adapts the US plug to the European plug or whatever plug. But because it's a universal, that doesn't mean you should just plug anything into there. All right, you have to make sure it is actually rated for that voltage. But anyway, so that's kind of the inside parts of a circuit breaker. And if we go to the next slide now, I have some different positions. So notice that we do have an on, a tripped, and an off. All right. So notice that trip is not quite lined up. Let me go back. Not quite lined up with on. Don't I have my drawing anymore? Now I do. Not quite lined up with on. All right. Not lined up with off either. It can be very hard to actually tell whether it's on or tripped. All right. And down here in the bottom corner, I have a nice little example of the tripped. So here you can see that we are in what we call the on position. Here we have the trip position. So it's just down just a little bit. And the reason we have that trip position is to help you see which breaker actually changed. All right. And also, we want it to be going to a trip position because we want you to be aware that it tripped. We don't want it just to go right to the off position and so you go, why don't my outlets work? And you go down, oh, my breaker's off. I don't know why it's off, but it's off. So you just flip it back on. You should really never just flip a breaker back on. All right. If the breaker tripped, it tripped for a reason. And then you have to figure out what that reason actually is. All right. Did it trip because you were just trying to pull too much power from it, right? You had a circular cell hooked up to a 15 amp one and you were just pulling too much power. Okay, not the end of the world. You know what you did. It's not going to burn the house down. You can flip it back. If the breaker didn't, if you don't know why it tripped, right? You're just like, why are my outlets off? You go down and you go, it's tripped. What's going on here? Then we've got a slightly bigger issue. All right. Is it because of something you did? For example, my family was visiting once, and all of a sudden our toaster oven wasn't working. I'm like, why isn't the toaster working? And someone's like, yeah, the microwave's not on either. I'm like, toaster, refrigerator, they were all off. I was like, what's going on? Like, why? What caused this? After thinking about it, I think we had the toaster, the hot water, the tea kettle, hot electric tea kettle pot, the microwave, and the refrigerator were probably all running at the exact same time, and they're all pulling a nice chunk of power. So because of that, we probably just too much power. We tripped the breaker. So once I went down, I found the breaker, we turned it back on, everything turned back on. It was fine. We haven't had any issues since. All right. So but now if it tripped again, then there was probably going to be a bigger issue behind that. It was, okay, so where's the problem? And then that's always a fun game of trying to troubleshoot your electrical. And problem here, is a problem there? Which outlet is it? How many outlets actually hook up to that breaker? It's always an interesting game. One of the things on my list to do is actually to turn all the breakers in my house off and go test every single outlet in the house so I know what is connected to what. I actually have already done that in the basement of my house, so I know where all the outlets in the basement, I know what breakers they go to, and all those things. But once we got to the first and second floor, I don't know what's what anymore. I've got some ideas because of having to turn things off for certain reasons, but I really actually have no clue what all goes to what. So that's on my list to do at some point. Um, so we do have those three different positions, and that trip position is very important because it helps denote to you which one is actually the problem child or which one had problems. Now, the other thing I want to point out to you on this page is inside that blue circle, you notice that this would be a single breaker wide, and we have double breaker there. All right. So that is something that you do need to, again, be kind of aware of. All right. Breaker panels are rated in the number of circuits they can handle. All right. And a lot of newer breaker panels, let me go ahead and go to my zoomed in. So here we have a nice little breaker panel that you could go buy at Home Depot if you wanted to. All right, you can see our breakers there. But anyway, so this is if we read the description, a 200 amp, 30 space, 60 circuit indoor main breaker, circuit breaker panel. All right, so it has 30 spaces, which means if you were to count all these, and not even necessarily count them all, but there's 30 places where we could put single breakers. All right, so you can actually over here see some single breakers, and we can also see some double breakers. So there are 30 spaces for single breakers, which means there's only 15 spots if you were going to do double breakers. So you can only put 15 double breakers in. The double breakers are that higher voltage. All right. And the other thing you'll notice about double breakers is they actually have a bar connecting them together. All right. So there, that one, you can see that bar pretty nicely. This wider so we can actually see the video, and let's slide that way. There you go. So that you can actually see that bar connecting them. Here you can actually see the backs or the sides. All right. So there would be those two screw terminals that you would screw your wires into. Down at the bottom, hard to see, but that's what clips into the breaker panel. All right, that's all the pictures they have for us. In this one, you can see the bar pretty nicely too, right there at the top. All right, so they're actually physically coupled together with a double breaker like this. So this type of double breaker that's 2 breakers wide is meant for 220 volts, or that higher voltage, maybe 240. All right. Whereas that double breaker that is in our presentation down there, that is a single breaker wide with 2 different breakers on it. So again, this circuit breaker that I was showing you guys is rated for 30, it was 30 spaces, but 60 circuits, which means you could put 60 different or 30 double breakers in it, like what we've showing you on the screen. What you see in this PowerPoint over here, you could put 30 of those in, which would get you 60 different circuits. All right, but it's only meant to handle 200 amps. Now, rule of thumb is you're not really supposed to have, if you add up all the values of your breakers, it's not really supposed to be over the rated current of your breaker panel or that main breaker at the top. Um, I believe that is code or something along those lines. I've never seen a breaker panel that doesn't have more circuits. If you add up all the numbers, that it equals more than what the breaker panel can handle or what's rated at the top. All right. I mean, if you have a 200 amp breaker and you're putting 60 different circuits in it, each one can be like 3 amps, or not even 4 amps, 3.5 amps could be each circuit. Like, they don't make breakers that small. So it's kind of this whole 60 circuit thing is kind of lying to you on that breaker panel I just showed you guys. So that is kind of interesting. All right. Now, so we do have some different classification ranges, and this is based on the amperage, so the current ranges. So you can see those on the screen, and your book will go into some more detail about those that you guys will be reading in chapter 9. We're skipping chapter 8. We'll come back to it. Don't worry. All right. So we do have some different ranges here. So 15 to 100 amp. Basically, that's all you're ever going to see in your traditional house, except for maybe your main breaker. Your main breaker could be a 200 amp or a 300 amp. All right. And what really that determines is what your electric company has run the wires to your house. What's that rating of those wire capability? So that is something that you do want to keep in the back of your mind. But otherwise, we can get up to 2,000 amp breakers. I mean, that's a lot of freaking power if you think about it. Now, when it comes to ratings, we already talked about how these are rated by ampere, all right, which is right there on the end of the little switch, all right. The other rating is the AIC rating, or amperage interrupting capacity, all right. And this tells us how much power, when that circuit breaker opens, the circuit breaker is able to stop. So if there's 1,000 amps flowing through that thing, right, the circuit breaker could handle it or not handle it, depending on what it's rating it. In this case, you can see our rating is right there. So 10 kA, that is our AIC rating. So this thing can handle up to 10,000 amps. It is able to open and break apart. All right, now if we're over that, it may or may not break it apart. All right, so that is something very important to keep in the back of your mind. The other thing is, and this is one of the glories of AC world, is because AC is alternating like this. All right, so if you actually put an oscilloscope onto your into your home outlet, the AC goes up to 120 volts, down to 120, up to 120, down, and we always call AC 120 volts at home. All right, that is actually 120 volts RMS, or root mean square. And what that means is we were trying to come up with a way that we could very easily compare the power usage of AC to DC. All right. Now, if you would actually measure this peak to peak, I believe it's actually closer to 144 volts, if I remember correctly. All right. But we still call it 120 volt AC because in the DC world, to have the equivalent amount of power, so 1 amp at 120 volts AC equals 1 amps at 120 volts DC. So to be able to qualify this more for the equivalency, what we did is, if we would really look at that arc, all right, so that's what an AC arc would look like. And DC would just be this perfectly straight line. All right. Now, if we would say, okay, when this leaves 0, hey, I changed my color. When this leaves 0 right there, and when it hits 0 again right here, you'll notice that, actually DC wouldn't be there. DC would be lower. Let me go ahead and quick fix that. Nope. Or DC would be more down here. All right. So you'll notice that in those areas, in the AC curve, we're filling this whole area in down here. And we go above that 120 volt point. All right. In the AC. In the DC, though, we have all this extra space out here at the sides that the AC doesn't. So there's power being delivered, more power being delivered at that point. So what root mean squared does is it basically allows us to say, okay, if we were to take all this extra space from the top and we, cut it in half and moved half over there and half over there, we would fill it in. And it allows us to very easily compare 120 volts AC to 120 volts DC. All right, so we can get the same amount of power output. So that's why we have 120 volts, and you might hear it called RMS or root mean square. However, I digress. So back to what I was saying. So the glory of AC is because we're alternating, the current flow is also alternating. Now the current flow may lag slightly, so you may see the current do something more like that, where it's a little bit behind the AC flow, which is fine. It's part of the gig. But because of that, an AC circuit breaker doesn't have to instantly break 1200 watts or whatever the magical, in this case, 2400 watts. All right. It doesn't have to break that perfect completely. All right. Because if that breaker trips right up here at max load, we only have to, in theory, get back down to the 0 point. And at that point, that arc will actually self-extinguish. So it'll go out because there's no more power flowing. There's nothing to keep that arc there. So as we actually approach 0, there's less power being fed to the arc inside the circuit breaker, which means there's less power flowing, which means it's easier for it to break that. So, very important fact that we are able to break that much easier with AC compared to DC. This is also why you should not use a AC circuit breaker in a DC circuit unless it is rated for it. All right. So whenever you are buying equipment, make sure it's rated for the right type of voltage, so DC or AC. But yeah, so I know I've gone way off of my my path of that whole 10Ka thing, but it is very important in the long run to make sure you're never going to hit that rate. And even at your house, you're never going to hit that rate. All right. In theory, your average homeowner, since we all have a master breaker in the U.S. at the top, which then leads to all of your little sub breakers down below it. So in my case, this is 200 amps. And then, this might be a 20, this might be a 70, that might be a 15, all those other things. So in theory, you actually have two breakers protecting your house. Now, for you to trip this main one up here, it's got to be pretty stinking bad. All right. That main one is meant to actually trip a little bit slower than all the ones below it. So that way you don't trip this one when you have just a dead short on something. You always trip these little smaller breakers first. So that way you don't have to black out your whole house if you do one little stupid electrical mistake. All right. You always pop one of the smaller breakers first. So that is kind of like cascading breakers. Now, if for some odd reason one of these gets welded shut, right? You've put so much power through it that you have physically welded those contacts together and that spring can't pull it apart anymore. That's when this 200 breaker, that main top breaker, will actually trip still as long as you're pulling enough power. So something to keep in the back of your mind. All right, now the effects of 60 hertz AC on the human body. And I do make to mention that 60 hertz is actually important here. All right. Here in the United States, we use 60 hertz power. If you go to Europe, they only use 50 hertz. All right. And there are some differences there. And if you're bored, go ahead and look up the difference between 50 hertz and 60 hertz. All right. And there is some difference. The biggest benefit to the 60 hertz is a higher frequency, which means our motor, induction motors will spin a little bit faster than we would at 50 hertz. There are some safety aspects to this. It really it comes down to what we kind of started with is what it comes down to. And I said there are some benefits with dealing with transformers and things like that. So we'll probably talk about that more next class. But anyway, here we have some different shock ratings. So if you get a 60 hertz greater than 5 milliamps. Now notice, I'm not even talking about voltage. All right, you can overall throw voltage out the window when it comes down to electric shocks and things like that. Voltage doesn't really matter. The only thing voltage does is it affects how easy it is for you to get shocked. All right. If you guys ever just take a 9-volt battery, you can touch both sides of that 9-volt battery with your finger and you won't shock yourself. All right, you won't feel anything. No power is going to flow. because the resistivity of your skin is so high on normal skin that there's not enough current flowing that you can feel it. Now, if you touch it to your tongue, which is moist, all right, at that point, then you will feel it because the current is the resistivity is a lot lower, so more current is able to flow. So overall, voltage doesn't truly matter. All right, roughly, I believe it's 30 volts. Is like the magical, like safe to handle and deal with without too much worry when it comes to bare hands and skin and touching both sides of the voltage and things like that. Over that voltage, that's when you will start. Your skin doesn't quite have enough resistivity and things like that you might actually start feeling shocks and stuff. So, but at greater than 5 milliamps, you got a painful shock. 15 milliamps or more, people will what's called freeze to the circuit. All right, and that means you get stuck to the circuit. Never touch somebody who is stuck in an electrical circuit. Cut the wire, like quickly with an axe or something, if you can. Hit the circuit breaker. Turn the switch off. Worst case, kick them. Don't grab them, because if you grab them, you could actually be like stuck back in the circuit. And I'm not saying maliciously kick them. I'm like, try to kick them out of the circuit, all right? Because your foot, your shoes probably insulated, those types of things, so that will help keep you from getting stuck into it. All right, and as we get higher and higher voltages, you're more likely to get stuck, or not more voltages, current, you're more likely to get stuck. All right, the other thing they'll tell you when you're dealing with things like multimeters and things like that is the one hand rule, which means only touch the circuit with one hand. Never have like a black probe in one and a red in the other, because if something happens, now you can become the path of electricity. So oftentimes you'll want to like clip the black wire to something and then probe with the red wire. So there's in theory not a complete path of electricity if you accidentally shock something. So you want to be very careful of that. At greater than 30 milliamps, we have some difficulty breathing. 50 to 100, you might have some heart failure or things along those lines. 100 to 200, definitely going to have it. And greater than 200, you're probably going to have some severe burns. And most likely your heart is going to stop or fibrillate. So you might be dead. All right. I know a lot of people who deal with electricity, not deal with electricity, but like who are engineers and things like that. And if you tell them, yeah, I got electrocuted, that means you died. All right. If you ever look up the definition of electrocuted, that means you died or your heart stopped. Most likely, you actually had an electric shock. So just one of those things to keep in the back of your mind. It keeps electrical engineers and things like that happy. Next, we go into a special type of circuit breaker, and this isn't necessarily always a circuit breaker. This actually could be just an outlet, but it's a GFCI, or ground fault current indicator, or circuit. I don't know why I have current indicator. Circuit interrupter. I need to fix this. Circuit interrupter. And I know I didn't spell that right, but I don't care. All right, so it's a ground fault circuit interrupter. And basically what this does is normally in your standard electrical cab circuit breaker panel, the white wire would just come right over here to this bus bar. And all of the white wires would connect here, all your green wires would be here, and all of your black wires would go to your different circuit breakers. All right. What a GFCI actually does is it actually connects the white wire, that neutral wire, to the circuit breaker as well. All right. And what this allows the circuit breaker to do is it actually monitors the current flowing in both the black and the white wire. And as long as they are equal or very close to equal, everything is fine. All right. However, if one of these all of a sudden, say the black wire has 100 milliamps and the red wire has 100, not 10, has 0, that means power is flowing from your black wire out through your outlet, through whatever, and it's coming back through this green wire. So instead of it coming back the white wire, which is what we expect, it's coming back the green wire. That means there is a fault somewhere on your system, and that circuit breaker will trip, or the outlet if it's built into the outlet. All right. So that will actually trip and turn the outlet off. And this is probably most often caused by water. All right. So it could be that you've touched the black wire, you're standing in a puddle of water, you're grounded, or your foot was grounded, or your hand was grounded, and you're shocking yourself. And that circuit breaker is realizing this. There's not enough current to flow to trip a normal circuit breaker. It's not 20 amps of power flowing, but if we go back, man, we only need 50 amps, maybe 100, 50 milliamps, maybe 100 milliamps to cause huge issues. So it's not enough power to trip the circuit breaker, but it's enough power that this thing goes, ooh, something bad's happening. I don't like this, and it's going to trip, and then it'll stop sending power out, which should then help you get you off of that circuit. All right. Um, so GFCIs. Now you normally see these, as I said, in wet environments. So bathroom outlets, they should have GFCI. Kitchen outlets should have them. Any outlets outdoors should be GFCI. Here it's saying greater than 6 milliamps difference between those two, and it will trip. All right. So not quite enough to stop the electrical shock, possibly, but enough to protect you. And then they have to trip in 1/40th of a second. 1/40th of a second, like 2 milliseconds. That's stupid fast, in my opinion. So, um, really nice big benefit there. But yeah, so GFCIs, and again, you may see them. Normally, if they're outlets, they're like a square type of outlet, and they have two buttons right here. And then again, you have your kind of your outlets over them. Those buttons are right in the middle. And the nice thing about GFCIs is what it says right here: push to test. All right, there is actually a resistor built into the either the outlet or the circuit breaker, which actually basically just takes the black wire when you push that button. So the black wire comes into that button, that wire comes up, goes through a resistor to ground, which say allows 10 milliamps of power to flow. Um, and this will then realize it, and it will then purposely pop the breaker, all right, or pop your outlet. So you can actually test them to make sure they're still good, which is something that you should do at least on a yearly basis, if not more often. Um, so this can cause problems. This especially can cause problems in our classroom because, as you guys might know, the black tables that you guys will be sitting at, there's outlets built into those right on the countertop. They're all GFCI. Each outlet itself is a GFCI, which is beautiful. It's a safety feature. But some of our trainers aren't wired correctly. They have a neutral and a ground wire, and on the trainer they actually connect them together. So half when you plug a trainer into the GFCI, half the wire goes down the neutral, half the wire goes down the ground. If we're pulling too much power, it will pop that GFCI instantly. It's very annoying, but it's just something that happens that we have to deal with. So we can't plug a lot of stuff into those tables, but there's a lot of things we still can as well. So ground fault circuit interrupter. There are a few other types of circuit breakers. We have a shunt trip, which is power flowing in the wrong direction. In our case, when we are doing a back-fed breaker, which means we have our breaker panel with our breakers in it, all right? Normally, power flows from the top down through and out to whatever, out to whatever circuit it is. If we have solar or wind turbine hooked up at home, we load our wind turbine here, and we're doing a back-fed breaker, that means we're actually putting power from the wind turbine and back to one of these breakers. So you have your main 200 amp breaker at the top, and then we have a little breaker down here, which will actually allow the wind energy to actually flow into your system. So a shunt trip would actually keep that from happening. We have arc fault, which detects continuous surges and spikes. We have switched neutrals. So normal circuit breakers, they only switch the hot wire. In a 240 outlet or 220 out breaker, sorry, we have those two breakers that are connected together. All right, both of those are actually hot wires. You still may have a white wire going to it and a black wire, but that's still hot wire, even though we have a white wire going there. So something to be aware of. There's non-automatic ones as well, which really aren't used. So circuit breakers are meant to protect your wiring. So are fuses. All right, so fuses are another overcurrent protection device. All right, fuses basically are non-reusable circuit breakers. That's all they are. Once a fuse pops, it's done. All right, so that is something that you do want to keep in mind. Cartridge fuses, which is this one up here at the top. This is going to be the most commonly used fuse that you guys will see, and we do use those in our trainers. All right, so you guys probably will pop some fuses. We'll have to replace them. It's not a big deal, but it's something to keep in mind. All right. When we're working in the industry and we're dealing with over 600 volts, we have to use fuses. All right, circuit breakers do not qualify at that point. Oftentimes at that point, you're going to see more of this like knife blade style fuse. And it will be in a big disconnect. So you'll have a disconnect like this with like a nice handle on the side. And normally there'll be 3 spots for fuses. Because it's probably, if you're at 600 volts, you're probably rocking 3-phase. So you'll have 3 different fuses, 1 on each phase. So that's the type of thing that's going on. So knife blade fuses, you'll see those. This plug type, this was the one that I was talking about, which is the one that we used to use in our household. All right. So that's the type of thing that we used to use. That you used to have a fuse panel in your house, not a circuit breaker panel. Anytime things would blow, you'd have to go down there and actually replace a fuse and throw it out. The biggest downside slash benefits I may say to these types of things was if your fuse blew and you didn't know how to, you didn't have another one to replace it with. A lot of people would put like pennies or quarters behind them, and that would like short circuit, basically bypass the fuse, which is obviously not really a good thing to do. But a lot of people did it because like, well, I need my power back on, and I don't have another fuse, so they would just throw something in behind it to allow it to short circuit. So not a good thing. I've also heard that these fuses aren't always the best. My dad had an apartment and the basement was flooded and the whole fuse panel, it was a fuse panel, was submerged underwater and the sump pump was still running. I mean, there is power, water flowing through that whole circuit breaker panel. Things should just be short circuited like crazy. But no, no big issue. Power is still flowing. Water wasn't conductive enough to run, I guess to pop the main breaker or screw up the transformer on the tower or things like that. So, yeah, big issue there in the long run. So that would be our old style fuses there. So I do have a lot of videos, but I'm not going to make you guys watch them with me because I don't think that is going to be a great opportunity for you guys. Let me go ahead and hit that button. So here I have fuses blowing in slow motion, so you can actually like see the wires break and things like that. We have a selective tripping option here, how they work, what's inside, again, how they work, different videos. So these are some really good videos that you guys need to go watch because they're really neat and they really kind of show you that the arcs happening and things like that. So this one actually I believe goes into like super slow motion. Um, yeah, I mean super slow motion. So you can see the very top, the contact opening and things like that going on. So, and then you can see that arc, how it treasured and all the other fun stuff. So you guys need to go watch those videos. They're really good videos about circuit breakers and how they work and those types of things. So, all right. So that takes us basically we're done with circuit breakers and fuses.